I hope that you took my directions here and referred to the last set of notes when answering this question. Can you or can't you tell? And hopefully you wrote that you can't tell based upon the picture, okay? Whether that is fresh or salt water. And how would you need to be sure? You could use a testing device, instrument, or you could take a sip and spit it back out again, right? All right, so we're on slide 17. And we're going to be explaining the effect of water temperature on the solubility of salts. So we talked a little bit about this in the last set of notes, only introductory level. Now we're going to go a little bit deeper into it, okay? No pun intended. Water, deeper. Haha. All right. As temperature increases, simply put, as the temperature, which these graphs are showing us for the most part, as the temperature goes up, x-axis, the concentration of salts also goes up. So that is a positive correlation, right? If one goes up, the other one goes up. Here, it's pretty much showing that for all of these. Now look, sodium chloride is the least affected by this. It starts at about 38, 36 or so, and goes up as the temperature goes up, but only slightly compared to the other salts here, all right? And this, so here they've expanded it so you can see a more drastic change for sodium chloride. And this isn't telling you exactly what they're talking about, but it's still showing you that solubility goes up with temperature, okay? It's rather simple. The more I heat water, the more stuff I can dissolve in it. The more solids I can dissolve in that water. That's how they make rock candy. Have you ever had one of those rock candy lollipops? They super saturate. They heat the water up very high, above like boiling temperature, so you can add more sugar, which makes more dissolve and makes it super saturated. Like a sponge, it's too wet. You lift the sponge up and the water's dripping out, okay? And then when they cool it down slowly, those crystals reform and stick to the lollipop stick, and you've got flavor in there as well as food coloring, and voila, you have a rock candy lollipop. So, slide 18, define the term salinity. It is the concentration of dissolved salts in seawater. It's how much salt is in that sample of water, okay? So for ocean, around the world now, the entire ocean, the seas, Atlantic, Pacific, Indian, and the Antarctic Ocean, all of those oceans, the big major ones, are average 35 parts per thousand. And to write parts per thousand, it's a 0 over 2 zeros. Looks like the percentage symbol, right? Well, what is the percentage symbol? The percentage symbol is parts per 100, right? Percent. Cent, like a century, 100 years. All right, anyway, but that's parts per thousand. So that's how you abbreviate PPT. The highest salinity, question on your notes, the highest salinity in the world of any body of water, natural body of water, is the Dead Sea. Over there somewhere. You can't see it. It's behind the M in Mediterranean, right? At 33.7% salinity, or that's 337 parts per thousand, or written this way, okay? Whereas this is 3.5% salinity. 3.5%. Because it's moved decimal place over one to go from thousands to hundreds, right? And the Arctic, which is up here, right there, see the light blue? Okay, that's the least, about 32 parts per thousand, or 3.2%. So your question is, why is the Dead Sea saltiest? Well, there's no new water coming in the Dead Sea. And any water that's there, it's evaporating, leaving behind the salt. All right? No new water coming in. Any water there is evaporating, leaving behind the salt. It's actually shrinking the Dead Sea. And it'll be a salt flat someday, unless we somehow get more water in the area. And in the Arctic, why is that the least saltiest? And if you said because of melting ice, then you are correct, because all that fresh water is being added into the ocean, which is reducing the salinity. Okay. Slide 19, freezing point of water. Well, it's pretty obvious to see that the amount of salt you add lowers the freezing point, okay? So freezing point, blue line, temperature given here in degrees Celsius. Notice how they're labeled and have units, okay? So this one would be, well, they included the units there, but don't do that. Just put amount of salt in grams in parentheses. And then over here, the units are missing, so that's bad. That should be degrees Celsius or degrees Fahrenheit or kelvins. But anyway, it's very simple to see. Salt water freezes at a lower temperature. That's it. Salt water freezes at a lower temperature, below freezing. And the more salt, the lower the temperature. Okay. So what's surface runoff? Surface runoff is when it rains, okay? And that rain falls on the land, which washes away the land into the water. These concepts are quite simple, okay? The opposite of that would be evaporating water from the surface or freezing water. Either way, you're taking out water. Putting in water, taking out water. And how do those change the salinity? Okay, now, runoff obviously is going to overall probably decrease the salinity. So the mouth of a river, the Amazon River, the Nile River, here in Florida, the St. John's River or the Loxahatchee River up in Jupiter, okay? Did I say St. Lucie River also? These rivers, that's up in Stewart and Jensen Beach, the St. Lucie River. Excuse me. These rivers washing into the Atlantic Ocean are going to reduce the salinity, but only right there where the river flows into the ocean. And then it'll mix further out. But if that water is carrying dissolved solutes, it's going to make the ocean eventually increase in salinity. And the ocean is, every year, getting saltier. We're not getting any new water on the planet, right? There's no water coming from space to our planet. The only water that's here is the same water that the dinosaurs drank 65 million years ago, right? So the ocean, the land is just continually washing into the ocean, so that's going to increase the salinity eventually, over time. And then, of course, melting sea ice will also add fresh water to the mix, right? Sea spray, fishes, the more fish, the more absorption of fresh water, leaving salts outside. We'll talk about that next semester when we talk about physiology of marine creatures. So removing water increases salinity. Done. You're taking away water, you're leaving the salts behind. And these are examples: evaporation, freezing into ice. And then also by adding salts and chemicals. So volcanoes, volcanism, will add chemicals that will dissolve into the ocean, making it saltier. Hydrothermal vents, we'll talk about those in the future. And then atmospheric dissolution. That's at the surface of the water, being stirred up by the wind and stuff, which is mixing gases into the water. mixing gases into the water, okay? Making it less pure. All right, slide 22. Describe the pH scale. Now we're going to do this it says in your notes, so there's no notes on this slide. We're going to do this in an online virtual lab, okay? It's called a PHET lab, a PHET lab. And it's just really simple. You may have even done this activity like previously, but because this isn't a major concept, but you still have to know what pH is and how it affects sea life and stuff. So right now, for all you have to know is 1 through 6.9 is acid, 7.1 to 14 is a base or an alkaline, and then 7 is neutral, and that would be pretty much pure water. Pure water is neutral, all right? But we're going to be doing an activity on this soon. All right. Demonstrate the use of litmus indicator. Same exact thing. We're going to be doing this with that. So both of these slides, we're going to be doing on that lab, that virtual lab, okay? And so you may have used litmus paper before. It changes color when you dip it into the water. Blue for base, red for acid. And there are different kinds. They turn different colors. It tells you approximately what pH the liquid is. So, all right. 24. State that oxygen has a low solubility in water. Because it does, compared to carbon dioxide. And it has to do with polarity. So make sure you write that in your notes. There's a line there that has to do with polarity. It's polar versus non-polar. So gases are the opposite of solids when it comes to dissolving. So the higher the temperature, the less soluble they are. So the temperature of the water increases, the carbon dioxide is going to leave the water. Less carbon dioxide, less oxygen. But oxygen is not as greatly affected as carbon dioxide. It still has a low solubility overall. Low solubility overall compared to carbon dioxide. You can easily dissolve carbon dioxide and oxygen, but carbon dioxide will be better by just taking a straw and blowing into water for like a minute. Bubble, 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 right? And then you can test the pH or the carbon dioxide concentration. Actually, it's the pH of the water, because carbon dioxide in water makes a very mild acid called carbonic acid. And the carbon dioxide from your breath dissolves very readily in that water, and you can test it really easily. Okay, so we're going to look at some graphs, some more graphs here. I told you know from earlier this week, or last week, that graphs are a huge part of this class, and we're going to be making them and reading them and understanding them. So, water temperature, pressure, depth, atmospheric pressure, which is atmospheric pressure. Well, not the same. Depth is measured in atmospheres. So, yeah. And salinity of the solubility of gases in water, and the implications this has for marine organisms. Whoa, Mr. Keene, we're talking about marine organisms now? A little bit, yeah. We are going to talk about them more in the future, of course, but all this physical stuff we have to get out of the way first, all right? But let's see what these effects can have on marine organisms. So, water temperature, for example. Remember, the colder it is, the more gases can go in. So colder water will have more oxygen. Yay for the fishies. The fishies will have more oxygen in the water. Warm water, fishies, not so good. All right? As you can see here, oxygen goes down as the temperature goes up. Pressure and depth, okay? Pressure measured by depth, the deeper you go. The higher the pressure, meaning the deeper you go in the water, more gases will dissolve because it's pushing and keeping that gas there. So pressure is increasing, and you can see carbon dioxide solubility goes up. It's denser. Atmospheric pressure. The greater the atmospheric pressure, the higher the solubility of gas. So, over here, pressure in bars and oxygen solubility going up, all right? So the higher the pressure, 4, more soluble. 2 is red, less soluble. 1, which is, bar is just a measure of like how many, don't worry, it's like how much pressure is being exerted by the air on the water's surface, okay? All right, that's a measurement. So the greater the pressure, think about it, it's pushing air, gases, onto the surface of the water. And so that's going to increase solubility. And then if I increase the salinity, there's less room for gases, okay? So fresh water, this black line, is going to have a higher oxygen content overall per temperature than seawater, this blue line and below. So more salt in the water molecules, less room for gases, okay? All right, slide 27, only 5 slides to go. Effect of water temperature, pressure, and depth. This is the same exact title, but moving on to why there's more oxygen at the surface, okay? So, you're going to have to be able to understand graphs such as this. Here we have depth in feet going at 0, so this is the surface. And see, this throws some students off, okay? You're used to 0 being down at the bottom of a graph. But typically when you talk about depth, you want to visualize a basin of water, right? Okay? And 0 would be at the top. And the numbers would increase as you go down. So please just realize that. All right. So talking about depth in feet, depth in meters. So this is depth on both sides. We should have just meters here, but that's fine. And then the concentration of dissolved gas is going up in this direction with the scale. Carbon dioxide's on the bottom. We know because carbon dioxide dissolves better than oxygen because of polarity. And the oxygen numbers are there, okay? And you can see, for the most part, they're kind of stable, but then there's a switcheroo at the surface, okay? So the deeper you go, the oxygen decreases. And it decreases to a point and then slowly increases here a little bit, all right? Then the carbon dioxide goes up, goes greater, right? And then slowly levels out to pretty much level. So let's read some of these questions, all right? So more oxygen near the surface. Why? Why is there more oxygen at the surface? Well, we talked about this. Mixing and atmospheric pressure, right? Waves and turbulence, they mix it up and add that oxygen to the water. Now, photosynthetic organisms also live near the surface of the water. And what are, like algae? What do algae, if they're photosynthetic, what are they making? Oxygen. Okay? So, but down here in the deep parts where there's no light, there's no photosynthetic organisms. So that's why the oxygen level drops. That's why the oxygen level starts to diminish in that direction at the deeper you go, once you get to a certain point, okay? This is not a drop. That's a drop, okay, that one. So oxygen decreases beyond 200 meters. Why? So that's, and of course the question to that was no photosynthetic organisms. I just said that, right? Okay. There are only respiring organisms like fish and jellyfish and things like that. So they're using up the oxygen. The organisms that live in this entire area, they're using it up. That's why it decreases. And of course, decay, the process of decay, animals that die at the surface and slowly sinking to the bottom, that also uses up oxygen. And then this is important. This may be a question on a paper. All of this is going to be questions on something. But you see that there's a slight increase. So from here to here, it's like 1, right? But then from here to here, it's like 2 milliliters per liter, okay? Why is there a slight increase there? Lower temperatures mean higher solubility from that previous slide. Lower temperatures and higher pressure means higher solubility. So the temperature is decreasing as we go down, which makes gases more soluble. And the pressure is increasing as you go down, which makes gases more soluble. That's why there's that slight increase right there, okay? And here's just another visualization of it. We haven't learned about these different zones, but I did mildly teach you about the photic zone where the photosynthetic organisms are. And you can see that once that drops in depth, this huge increase. And then this is just the difference between oxygen and phosphate, actually, not carbon dioxide. So you can, not oxygen, and again, not carbon dioxide. So you can compare multiple different things using these types of graphs. All right, 29. Explain how water temperature, pressure, and salinity affect the density of seawater. Low temperature, denser water. Colder water is more dense because the particles are closer together, right? Anytime there's particles in any substance are closer together, you're going to get denser substances. Until water becomes a solid, right? That's the special thing about water, that it becomes less dense, but for the most part, lower temperature, denser water, closer together. Increased pressure, pushing those molecules closer together, more dense. The density of the water increases as you go down in depth. And of course, increasing salinity. The more stuff I pour into the water, the more stuff there is, so the denser it is, okay? And this is just a pretty complex diagram showing a temperature salinity diagram. So as the temperature goes up over here, all right, you can see the changes in the salinity are, it's going down. Okay. Lines, sorry, that's density. Sorry. That's density going down. Okay. Temperature goes up, salinity would go up, right? The density goes down. All right. This is the salinity down here. The lines mean density. Speaking of density, this is how you mathematically convey it, all right? And we've all learned this, mass divided by volume. I always like to think DMV, like the Department of Motor Vehicles, okay? And this is a nice little tool to use. So if you are trying to determine what the volume is, the V, and you're missing the V, but you have the M and the D, you're trying to determine the density, which is density equals mass divided by volume, or if you're missing the M and you have the D and the V, this is what you do to determine the M, okay? So, and the units given for each one of those. So the units are always in kilograms per cubic meter or cubic centimeter. Grams per cubic centimeter, okay? Grams per milliliter. It's always mass over volume, okay? And of course, mass is always given in grams, and volume is always given in cubic centimeters, cubic meters, cubic kilometers, or milliliters, liters, kiloliters, okay? Density of ice causing ice to float. We talked about this already. We know that the hydrogen bonds expand those water molecules out, which decreases their mass per volume, decreases the density. There's less atoms now in the same amount of volume. They've expanded. That's why maybe you've heard about ice. Okay, many of us have probably put water bottles or soda cans in the freezer and then forgot about them and came back and the can exploded, or the water bottle, popped, the bottom popped out, because ice will expand about 9% of its volume when frozen, about 9%. So, and because of that less density, it floats, providing habitat for polar bears and bearded seals and Adelie penguins, okay? If it were not for this ability, then these organisms would never have adapted this way. And because of global warming, climate change, right? Our temperature, our planet is heating up. We're losing some of this, and so some of these organisms are struggling to adapt. And this is one of those rare instances where we have two different topics on the same slide. So, importance of ice floating as a thermal insulator, okay? So, if ice freezes, right, and stays on the surface, doesn't sink, then it's going to form almost like a blanket over the surface of whatever body of water that we're talking about. It will reflect sunlight, it will trap heat underneath and keep the below water from reaching those freezing temperatures. It will provide habitats for algae and penguins and seals and bears, oh my, all right? And other terrestrial mammals, or at least semi-terrestrial mammals. Okay, so mixing. All of these things in the water, the temperature fluctuations, the different layers, the salinity gradients, form these things called, and these are very important words, and you have to know the difference between these three, a thermocline, a halocline, and there's something called a pycnocline. Oh, there it is. Pycnocline, okay? And so a like a thermometer is temperature, right? Temperature, rapidly decreasing temperature. So if you look at, where is it? This is for salinity. That's a halocline. This is a pycnocline. Here it is. Thermocline and halocline equal pycnocline. Okay, so, yeah. So the thermocline's here. This right there is the thermocline. It's a rapid decrease in temperature. Halocline is a rapid increase in salinity over depth. So temperature goes down, salinity goes up, and then the pycnocline is an increase in density over depth. Temperature's dropping, increased density. Salinity is increasing, increased density. Together, they make the pycnocline together, okay? And those are just terms that you have to know. Now, mixing at the surface due to wind and waves, currents and upwelling, will have an effect on the layers where this changes, it shifts, but it's always there. Mixing at deeper, and we haven't talked about what upwelling is yet, we'll get to that in the future. Deeper depths due to dense water sinking and deep currents at the bottom that flow. So these aren't perfect like this, but they do get mixed, So that's those words, thermocline, halocline, and pycnocline, not pinkocline, like the color, it's pycnocline, okay? Just like it's spelled. are all based upon cold is denser and more salt is denser, okay? And you're gonna have to be able to recognize what this is and how to read it in the future. We have an activity on it. And here's your last slide. This is asking you to explain what's happening, I believe, in your notes. I think maybe the differences between these two. So here you have a cold environment and what's going on with the thermocline, okay? You see the temperature down here and the depth here. And then here you have a tropical climate, okay, versus polar. And you can see the differences between the two. So the shapes of the thermoclines. So just describe what the difference is between the two, okay, in your notes. And then you're done with part 2.